Hi, everyone. Why are we bringing up imaginary numbers now? Because we're going to look at all complex zeros of a polynomial function, including potentially imaginary zeros. So for example, find all complex zeros of f where f of x equals x squared plus 9. Well, let's set y, or f of x, equal to 0 and solve for x. X squared plus 9 equals 0. Let's subtract 9 from both sides to isolate the square. And the square root method still works. We can say that x is plus or minus the principal square root of negative 9. The principal square root of negative 9 is 3i. So x could be 3i or negative 3i. Now the question was to find the complex zeros. So it would be enough to say that the complex zeros are 3i and negative 3i. In fact, if you were to just box these in, I may well accept that. If you're asked to solve this equation, then you should write the solution set. But notice here, we have imaginary solutions to this equation. X squared plus 9 has two complex zeros, both of them imaginary. And notice they're related how? The complex zeros are complex conjugates. They are complex conjugates. And we're going to come back to that. All right. Next up, find the complex zeros of f, where f of x equals 2x squared minus x plus 3. If you try to factor that old school, to no avail. So we may have to resort to the QF, the quadratic formula. Now, it's helpful to identify what A, B, and C are. What are A, B, and C, the coefficients? Well, the leading coefficient, A, equals 2. Now, this is where a lot of people make a mistake. B is negative 1. Be careful about that. B is negative 1. And then C is 3. All right, let's apply the quadratic formula. You should remember this. X equals the opposite of B, so it's going to be the opposite of negative 1, plus or minus the square root of B squared minus 4AC. Remember, this was called the what? This was called the discriminant. This was a discriminant. And in fact, if you were to ask yourself, can I factor this old school? You might have wanted, that is factoring it over the integers, you might have wanted to work out the discriminant first. And you'll find out that the discriminant turns out to be a negative number. It turns out to be negative 23, which would tell you that you could not factor this thing old school. And you would have had to pretty much resort to the quadratic formula anyway. The thing is, if you work out the discriminant, you're ready to stick in the negative 23 right there in the radicand. So we pretty much had to use the quadratic formula anyway. By the way, it's the opposite of b, the opposite of negative 1, plus or minus the square root of the discriminant is negative 23, all over 2a, twice 2. When working out the discriminant, be careful. It's the square of negative 1, so we have positive 1 here, minus 4 times a times c, so it's minus 4 times 2 times 3. 1, and then minus 24, that gets you negative 23. Remember, use grouping symbols here. Remember, the square of a real number is never negative. Use grouping symbols here. All right. The principal square root of negative 23 can be written as I root 23. Root negative 23 should be written as I root 23. Now, very often, if you're asked to find the complex zeros, we may be okay with this, but the thing is, over here, especially if I ask you to find the zeros and write them in standard form, okay? When in doubt, you might want to be safe and write the zeros in standard form. So here I split the fraction at the plus minus symbol, right? And then I pop out the I over to the right. Technically, the I should be over here to the right. So in standard form, the complex zeros will be 1/4 plus or minus root 23 over 4 times I. By the way, up here, you could have written this as root 23 times I, but what's the problem? Way too many students extend the radical too far. This would be wrong. So to avoid that, that's why I put the I in front to the left. But if you write this, that's fine. Okay, so next, we are now ready in section 2.5 to talk about finding all complex zeros of polynomial functions. 2.5 is big. We hit that next.